Okay, perfect. Hey folks, we are live. Today we are going to discuss about the internals of levitate and how we handle the high cardinality. We have Piyush Sharma, CTO at Last Nine. He is going to talk about internals of levitate as well as the architecture of levitate. Feel free to post questions on the right hand side in the chat. Uh, we would love to take those questions after this session and also share the feedback with us. So, yes, let's start. Piyush, over to you.
Yeah. Uh, so a lot of times we get asked this question on how Levitate handles cardinality at a scale that it does. And so this talk, I wanted to do this as a single talk, but the more I went into the depth of what we have to share, it turned out to be inappropriate to condense all that information in one single talk. So we've broken this into three-part series. This is part one, and there are two more parts to it. And hopefully, if you would like to know more, and let us know, and we will incorporate those things in part two and part three as well. So here's uh, a very quick recap of the journey of a metric, right? And I always imagine metric to look like the smallest tuple. Is that smallest cannot be broken further piece of tuple, which says a smallest recording that I have for a span of time, not a point of time. Big difference. Recording is always for a span of time. It says for these X number of seconds, for this many dimensions, I hold a value. It is like the most smallest subatomic particle of an atom cannot be broken further. Once it has been trapped into those 15 seconds, you cannot break it further, or X number of seconds, or Y number of milliseconds, depending on the fidelity and the resolution at which you want to record. The lower you go in resolution, the more data you will generate. The higher you go in resolution, the less data that you'll generate, but the opaqueness will increase. Let's double click on this. If I hold a record which is only for an hour worth of data, now you can never drill it back to a smaller subset of time because now it is an hour worth of data now. Now, but this is not where cardinality grows. Cardinality grows elsewhere. This is just amount of data. This is just number of float samples. By increasing the number of recordings, you're basically just adding one more point into the storage array. That doesn't hurt much. Here's a visual part of it. This is something that a lot of people who have used Prometheus associate with this. I'm not going to spend too much time on this one. I will only spend time uh, on that later. Yeah. So let's look at this part of the entire spectrum. This is what you're used to. There's a part called metric name. There's a part called dimensions. Then there is a timestamp. One big classification to be made here. Most of us, when we use metrics and when we use Prometheus's world, we assume that it's a timestamp of the of when it was emitted, but actually it's not true. It is the timestamp at which it was reported. This is a very distinct understanding to be made in it. It is not the time of the event because it is not a particular time that a metric holds. It's a span of time, and if you have to represent it in a single value, it means it's a time of reporting. At 8:01 p.m., I am reporting for the previous minute worth of recording. Now, this distinction is very important to have because most of us get it wrong over here. But that's not where the cardinality grows again. How does cardinality really grow? Let's take an example. I'm not going to spend too much time on this, but think about it. Here's a metric. We have a bucket, we have a mode, which is card payment. Now, if we want to dwell further on the number of mode that card can have, card, bank transactions, direct debit, etc. Now, this cardinality growing. In addition to this, I also want to start recording status. 1, 2, 3, 4, 5, 6. It's multiplying. Then I want to add gateways to it. I want to observe more and more into the same metric. This is called the dimensionality of a metric. So, take another example of it. I want to measure physical attributes of something. I want to add more and more attributes, subsections to it, sub-classification to it. Another sub-classification could be I also want to record the payment completion seconds, but now per device, which is either a mobile or a web. I want to do further. I want to keep asking more and more questions. What processor was used? It's the same recording that you're doing. But if you see, you're going granular. You're going you're going further granular into the kind of observations and the kind of questions that you want to ask. We are not increasing the number of recordings, which by time, we are actually increasing the number of recording by something else, by the amount of attributes that the reading is for. This is called dimensionality. This is also called cardinality. And this is how it grows. Let's do the maths. When we started with, when we record something and we said we only have 6 modes to keep, our cardinality was 2 modes, 6 modes multiplied by a bucket in which we have actually taken a record of the number of, if you look at this way, the number of the time that we'll split into, we'll say these are 20 buckets that we're going to keep of time in which we'll keep recording. It's also very important because we're basically building a distribution of the latency over time. Now, 6 modes, cardinality is 120. We add 8 status observations to it, cardinality becomes 1,000. We start tracking gateways. Assume we are using 3 gateways. The same data will now be split across 3 gateways. And to be able to answer which gateway is wrong, you want each gateway to send its own observation. Cardinality reaches 3,000, give and take. You add a device type to it. Device could be any one of those iOS 13, 12, etc. It suddenly reaches 25,000. You add a processor type to it, and this is closely, if you look at it, this is reaching 100K. That is a total of 69,000 combinations being reported at every interval. Every interval. Now, if it was a 15-second interval, if it was a 1 minute interval, that's the number of combinations that are actually being supplied as readings, all for just one metric right now, which is payment complete seconds. There are going to be other such metrics into the system, which are constantly making that way in. You start multiplying those, you build a mental model of that, and you realize even if I have 10 important metrics to be captured, just 10, I'm not adding any fine observation to this to say what version number of the software, because you really want to use this information to understand that, oh, did my recent deploy or did my recent push break it? To answer that question, you would need additional attributes as well. But in absence of those itself, this number is just touching 100K. This is 100,000 just for a metric. You have 10 such metrics, makes it a million. This is how cardinality grows into a database. Some people also call it active time series. You would have read this very fairly, commonly across the internet. This is the terminology that they use. Now, but how do we deal with this? Now, this cardinality almost becomes inevitable. Well, inevitable because why do we do build observability data lakes? We build observability data lakes because when things go wrong, we want to ask it a question. We want to ask, as a part of our debugging, a quick debugging exercise, where did I go wrong? When did I go wrong? Which part of the system is going wrong? Like if I tell you right now, hey, the payment system is degraded, quite naturally you would ask which part of the branch of the code base or the release is degrading. You want to get down to the question, and the best answer to this would be, the worst answer would be, oh, something's going wrong. The best answer would be, for the recent most deploy that happened, version number 0.12 of your software, iOS 13 is failing for payment transactions that are happening via MX processor or Visa processor and are going through this particular gateway. This is the finest debugging statement that you can build. And all of this can actually be built just using metrics. You do not even have to go so far to use hunt through log lines. This can really supercharge. This can really supercharge the time that it takes to answer these questions. So a good amount of cardinality investment is always going to help you with two things. One is the mean time to debug a problem. And the other thing is to actually improve the quality of software, because metrics can actually stay in a system for a longer duration. You can actually compare them over time. Logs are so expensive to keep. This is why people invest in observability lakes. So it is important that either we stay oblivious or opaque to such questions. But if we have such questions, we will have to deal with cardinality. And this is where it becomes important. But what we have learned from our experience with these systems is these dimensions only keep growing. Questions surface area never reduces. It's a one-way street. When I unlock this potential to multiple stakeholders in an organization, it's no longer just a DevOps team that's going to look at it. Product team is going to look at it. Engineering teams are going to look at it. When a, when a lake or a system which can answer these questions at that level of fidelity, at that level of granularity, there are multiple consumers of the system that come by, and they ask more and more questions, and they never reduce their question. I've never seen anybody who tells me that, okay, I'm great knowing one time that the mode or the payment or the processor was bad, and here onwards you can actually stop this information. No, there's a desire to know more and more, because this becomes a part of your daily culture. Another thing that we know is changing dimensionality requires engineering bandwidth, because these are data points which are no longer just being emitted automatically from a prom node exporter or something. These are coming right from the code base. The important metrics are the one that come through the logic that you own. And when you own that logic, you have to make an investment to make a change. And it always comes in a it's path of an engineering sprint. So whenever you require a change in dimensionality, it's always going to land back on the sprint cycle of an engineering team, which will say, well, one more sprint, two more sprints. So there's latency there. So traditionally, what people do is they go slightly greedy about it. Here are the 10 kind of fields that I may will need at one point of time, because I don't want to keep going back to engineering team to answer these questions. So usually cardinality increases in massive bursts. It doesn't increase linearly or discretely at one slope, like today is 10, tomorrow it's 100. No, it actually, each time that there's an outage and you realize I got 15 more fields that I want to monitor, they all come in a flurry and the cardinality takes a huge jump. I've never seen it grow linearly. So it never gives you enough time to react. There's always wastage of data. Now, because we are always going to be greedy and ask more questions, there's always going to be wastage of resources, which means at any point of time, you may have more cardinality than what you actually need, because you fear you don't know the questions that you may ask later. And to provision for that, you always have this buffer of, oh, I may need this information tomorrow. I may need this information tomorrow. It's like logs for that matter. You have logs because you don't know when you need them tomorrow. But when you do, you wish you had more. That's always the catch there. Different metrics will have different needs. Some parts of the system will say, infrastructure team would say, well, I'm done scaling. I don't need this metric. Payments team, media team, consumer behavior team, user behavior team, all of these teams will require a larger horizon, and these horizons change. In fact, as you go towards the top, towards more executive decision making, where things actually move slowly over a quarter, you may see people want to maintain metrics for the service level objective metrics. They are retained for almost 6 months as well. 6 months, nobody cares about pod data for 6 months. So you fundamentally see it's the same observability data, but at different layers of this, different kind of information requires different kind of attributes to it, different tenets to it. Tenets are performance, tenets are guarantee. Well, if I say one of these days, if I say, well, hey CEO, I cannot give you service level objectives because my metric lake has actually gone down, takes no, will not take no for an answer. But well, pod data went away. It's fine. We got 10,000 of those. Different scaling strategies as well. Now, to be able to tackle all of this, because we have got different attributes of different parts of data, because effectively it's not the same data anymore, different teams come up with different lakes in a system. And before we realize, because there's no fundamental ability to tackle this problem at a ground level, we end up setting different databases. It's very common in companies that you would see, oh, my product metrics or my application metrics or my business metrics sit in this database, my infrastructure metrics sit in this database. We got a DevOps team of small 2, 3 people, which has never seen the infrastructure metrics go down. Very common thing. But product metrics, oh, well, we hold them. We protect them really nicely. And these are all different shards. Then you will see a data science team, which is now plumbing another data lake, which is a consortium of the information and knowledge that comes out of this. Could have been done simply if there was one single database which could do it. For a moment, I want you to imagine BigQuery. For a moment, I want you to imagine Redshift. For a moment, I want you to imagine Hadoop. You remember These problems are long solved. They're done. People don't invest time building these lakes anymore. But when it comes to observability, we are still doing it this way. Because fundamentally, I think we lack an ability to tame cardinality at a high scale. And this is, I think, where Levitate actually, and this is the part which Levitate tackles head on. We want to make sure that you got workflows which can allow you to stay on top of cardinality and allow you to make those bold choices that here is a lake. I want to put all my data in here, which matters to me. And I don't have to spend time and effort creating these smaller fragments. We almost end up being penny wise and pound foolish there. Got so many of these investments of X needs to maintain, Y data needs to maintain. Bring that all together, make it just one. The wrong choices that we have made in this war with cardinality today. We all chase, hey, build the fastest and the cheapest metric storage engine. But come to think of it, we don't realize it. We don't need it, right? Because every single data has different tenets. So the need is not to make everything fast. The need is to basically treat everything as different. We need workflows for managing high cardinality. We don't have to buy the most infinite or most expensive engine as well. This workflow, what do we mean by that? Let me double click on this. But before I get to that, here's a quick primer on the life cycle of a metric. A metric goes through these stages. You start with an instrumentation. Now, this is where you will use your SDKs, your language libraries, your node collectors, node exporters, OTel, whatnot. Then it reaches an ingestion stage. Once it reaches an ingestion stage, there's some stuff that you do around it, which is relabeling, dropping, yada, yada, other things. Then you put it into storage and then you query it. It's a four-stage process. Each of this process has its own attributes of processes that are run on top of metric data at that point of time. Now, if I have to take a guess, where is cardinality best handled? Do we handle it at instrumentation? It would mean that I have to go back to the developer and say, reduce cardinality, increase cardinality. We just spoke about that part. This is a painful exercise. It interrupts your feature development. The more I interrupt a developer to keep changing it, the more I'm basically taking away from features. We are robbing Peter to pay Paul here. I want to spend my entire time, my engineering team should only focus on building features, business value features. I don't want to land at their desk every single day. Hey, could you tweak this? Hey, could you tweak that? Hey, could you tweak this? No. If I've reached cardinality at the time of querying, I'm under an assumption that my storage engine has now an ability to handle billions, which means I've actually spent that much money. And what if I end up asking this question? Oh, we accidentally bumped up this cardinality at the time of querying, but the damage is done. I've already scaled the system to support that much. I've spent that infrastructure and it was linearly scaled because all databases work that way there. It's too late and it's too expensive. So the only place where cardinality really workflows can be handled is the ingestion stage and the storage layer, because that is where you are still on top of, you're not committed yet that I'm going to save all of this. I may save a different version of this data. I may not even need this cardinality, or I need different views out of it. We'll cover those workflows. This is what Levitate shines at. And now we start diving into the details and the depths of it. Levitate is broken into four pieces, and each one of this belongs to the different stage of the problem. The first part is a Levitate time series gateway. Second is a Levitate aggregation unit, and there's a tiered reader and there's storage units as well. And for the interest of time, in this particular talk, we're only going to the depths of Levitate time series gateway. The remainder of the talk will cover about the depths of each one of these and how do they plug into the system. All these systems have been designed in a pluggable manner. What we mean by that is a Levitate time series gateway solves all challenges that happen at the ingestion layer, which originate out of high velocity, high volume cardinality data. The way these things go down, or the way these things increase the bill or the effort, or the when it's either cost in form of effort or in terms of money, which you need to keep pumping in to make sure that the system is up and being able to answer these questions. All those problems that happen at the ingestion layer are taken care of on the Levitate time series gateway. Beyond that are other workflows. So I want to start with that. At what cost? By doing things the right way. At some of the places where we have installed this, We are able to actually do this in 95% lesser RAM, 67% lesser CPU, and the commitment that it never goes down. Now, down is actually a very ambiguous thing, right? Because think about it. I'm going to walk you through a use case. As we say, hey, you can actually do so much cardinality. What if at the instrumentation phase, a developer accidentally commits a URL with the get parameters? Each URL is going to be unique. Now, what should have been a million cardinality becomes billion cardinality. Is this a use case that we desire for? Probably not. But that cardinality is still going to hit it. It's going to bombard the system. It's going to bombard the system in a way where things may just go down. It was one metric which actually saw a surge, but it may end up bringing the entire system down. That is the state of the affairs that works right now, which is why it's important to split this into two parts. Here's an architecture diagram. We will share, we can always download the link to our slides if this is unreadable right now. And a lot of this information is already available on our blogs as well. We'll share that. Let's dive deeper into this time series gateway here. This rate control problem. What is the current way of reading and saving this data in all systems? There's an input metric stream. You write that data into a time series database. There's a Prometheus read query that comes in. Now, imagine a situation where this surge has happened. Your gateways, obviously, you cannot infinitely scale. I mean, one may say, oh, X components or X databases provide Y agent, Y gateway, Y traffic. They're not infinite. You're not going to build a system at a AWS Lambda which says that send us trillion or send me a million. You've got finite money. You got finite money to spend on to logical business problems, not build an infinite database metric lake here. Now, when a surge happens and the system crumble, the data is not being able, it's not being written to the time series database. There's a lag there. Now, because of one metric, you'll experience a lag across all your observability. As a net result, either there's a blackout or alarms go off because they do not see any data. This is a standard practice that happens because there is no ability to have rate control mechanisms. The first thing that we built in Levitate Gateway is actually a way to build rate control. Now, I want to add some more layers to it. There are flow control problems as well, which are about data and compute. There are locality control problems as well. But the first one that we tackle is a rate control. Now, what does a rate control feel like? Rate control means imagine there's a surge in this metric, the one that we just discussed. I may take multiple actions basis of this. I may halt the metric that is under duress. We may want to report the metric to the right team to say, hey, this metric is about to reach its cardinality. What was to do about it? Should we allow this to happen? Should we allow this to be ingested? Or should we block this out? Or should we only send a part of this rate control? We want to take a we want to make sure that every single metric that is coming in has this ability to identify itself and walk through its own gates of allowing and not allowing, so that a noisy neighbor does not bring down the entire system. Any distributed system, multi-tenant system has this problem. Now, when there are multiple metrics and each metric may belong to a different team, it is important that one team's metric does not bring down the entire system's observability. You want other rate control mechanism that once a problem has been solved, maybe there should be a concept of quota, which says, okay, now I can allow more, now I can allow more. And this quota must only replenish with certain actions that have been taken. An action could be a wait period of time, an action could be a scale up in infrastructure, action could be an approval as well to say we must need this cardinality to go in. This is the levers which are required to make sure that the system can continue to operate as a platform, as a system in itself, without facing constant downtimes or degradations because of certain spike in the behavior of data. In an abil- in a bid to do this, you need an ability to basically count the cardinality per metric. Now, let's split this metric into multiple parts as well. You could build the same lake for your prod data, for your staging data, for different clusters of data as well. So it's not a single metric. A single metric has different origins and shape as well. For each one of those, you must have this control mechanism that is available. For that ability, we must have first an fundamental ability to count this at that massive value. Secondly, be able to differentiate the freshness or the staleness of it. Think about it. When we say cardinality, I was already observing 100 users or 100 endpoints. Suddenly, somebody made a change, or gradually, sudden is not the problem here. One makes a change where one part of the system, a newer version, or in alpha or in production, whichever way, the get parameter starts showing up. Now, because of this, the existing workflow should not break on what was already coming in. It's only this newer garbage that is actually polluting my system must be stopped. So there must be a fundamental ability to identify new versus old, which goes missing. And we must be able to do this without locks, mutexes, or semaphores, or massive impact on CPU and RAM. We don't want to solve this problem by provisioning more and more infrastructure because our bid is to build a system. It cannot be that, hey, we need 4x more infrastructure to be able to solve this problem. Almost to a degree where we're saying this is anti-fragile to scale. These rate control mechanisms, these are like circuit breakers. They kick in when the system is under duress, which means their best performance actually comes in when the system is under load. So there's anti-fragile. These data structures probably or these mechanisms will not even kick in on the regular workflow, but they kick in when the system is, and they must perform better when the system is under duress. We looked around at all the databases that exist out there and the way they handle it. And there's a list of traditional methods that have been solved. There are probabilistic data structures for it, Bloom filters, hash tables, rolling bit maps. We have a blog post for this. We'll share the link. All of them have fundamental problems. Neither of them have tackled the problem head on to be able to solve this per metric, to give you that control which is available at per metric level, or they are marred with lock contentions. You try to do them at a scale, and you'll realize that the amount of CPU and amount of wastage that starts happening in resources is beyond the roof. Or there are certain data structures which actually lack even the ability to define freshness versus staleness. What Levitate Gateway does, who invented a new way to deal with this, which is a coarse mode and a fine mode. We basically, the gateway, and these are all configurable things at the back of it. And at any point of time, a small spike, a small rise is ignored. There are heuristics which basically take into the factor that if there is a sudden rise in cardinality of something and it reaches a certain limit, a threshold, where we detect, hey, this is where something can actually blow off the roof, the counters switch from coarse mode to fine mode. So that precision of counting of cardinality only kicks in when a particular metric is under duress and it has switched to fine mode. Fine mode is precise mathematics, where we count, we basically become very precise and calculative and clinical about what cardinality is coming in. In coarse mode, we basically use a combination of probability and we use a combination of rate control mechanism to like, okay, it's fine. This is the amount of data that can come in. As long as it is within this, we don't need to count. And once it reaches fine mode is where we start counting. Once the rate subdues, it goes back into coarse mode. And if it hits a certain limit, which is a hard limit of the system, which is defined by the capacity of the system as well, because no system has infinite capacity. It's a capacity that you define, it's a capacity that you provision, it's a capacity that you pay for. When I say pay for in terms of your allocation, that this is the amount of money that I'm willing to spend on this problem. When it reaches that limit, it blocks it off and it gives you that ability to decide what to do next. But the rest of the system doesn't get affected. All the other metrics are probably living still happily in their coarse mode modulation. The switch of coarse mode to fine mode every time there's a burst, which is unfathomable by the system, is what makes these gateways highly scalable. And this is what allows massive reduction in the resources that are required. This is one of the ways. As a net result, what it just doesn't unlock is not cardinality, is not total cost of ownership. It also unlocks focus. You don't have to look at every single metric. The system will only tell you what to focus at. The system allows you to buy your attention towards the right problems. You no longer have to go through these charts to understand, oh, X cardinality, Y cardinality. It's a waste of time. If it's all working well, why do you care? What you care for is what are those metrics which may breach because they require your immediate attention. And if you've failed to act in time, what are those metrics which have already breached? And these are the only two workflows that you care for. Rest of it is almost irrelevant because what is working well, nobody wants to debug that. You only want to debug the parts that are not working well. So the system, by this smart usage of coarse and fine mode, every time something hits a coarse to fine switch, you get an alert for it. You're able to track it down. At this point is where the cardinality became suspicious that it may about to breach something. And this is where it has actually breached it. Now, how do we achieve this performance? These gateways are actually built with embedded queues as well. So when there is surge, all the data is actually buffered and it does its own magic of making sure that it's all done that way. And in fact, we have done some innovation here as well. We save a lot of round trip on byte encoding and decoding, and it only, I mean, uses constructs of network packet deserialization and serialization to make sure that we only spend a very little amount of time on already compressed data because what is coming in from the network stream is already compressed, so we don't have to do it again. As a result of it, we're able to see massive reductions in latencies as well. And it's a like we are able to actually ingest in milliseconds here. And this is what Levitate Gateway actually unlocks at a rate control level. But we spoke about these levers. Once cardinality is hit, what are those levers? Those levers could be we drop the metric altogether to say, hey, this metric is corrupted. It makes no sense. There's no point ingesting it further. We got to fix it. Save the storage, save the rest of the system from duress. It's a point in time live action that we can take, or we just drop the extra cardinality. Whatever is coming in continues to come in, but anything which was over and above, we don't want that to pollute the system because it's extra. It's going to pollute the system. It's going to strain the system. What do we do about it? We can also define to move it elsewhere. Now, when I say move it elsewhere, there's a very tricky part. On a running system, I only had one database. What do I mean by move it elsewhere? Now, this is where Levitate becomes a warehouse because a storage system is not just one. You could have very specific different storages for high cardinality metric, for different kind of metric, for metrics which require different performance, for metrics which require different guarantees based on the quality of data, based on the volume of data, based on the velocity of data as well, it could be, or in business importance of the data. This ability to move it elsewhere requires this fundamental ability in the gateways itself to basically have flow and locality control. And this is where the flow and locality control constructs come in. Because at the gateway, now you want to be able to send this data to those rightful storage units, to those rightful, meaningful processors behind it. And this is what is unlocked in flow and locality control. Flow control is also required because you want to bypass points of failure. Now, if you go back to the original thing, these are these gateways, they are stateless. They send the data back into a certain storage unit or an aggregation unit. Now, if one of them is under duress, you want to bypass it. You want to move to the other one. And this flow control is essential to make sure that you don't keep hitting the same path. Locality control as well. And we will cover strategies of it. Three common strategies which are available for such things, and we know this from our from rest of the system as well, is replication, load balancing, and sharding. These are the three known methods. Let's cover them one by one. What does replication look like in flow control? And this is a classic methodology that we have seen most databases or most time series databases that we have actually seen out there which cover. They follow a very simple strategy of replication, which say bring up X number of nodes, all of them alike. They all look the same, which means when you have to scale one, you have to spend the entire amount of money at number of replication factors twice of it. So even if I have to scale my payment failure rate metric, which sits in one of these nodes, I will have to pay the same amount of, because it's there in somewhere, right? It's a part of, let's say each one of these nodes become 2 terabytes, 2 terabytes, 2 terabytes, and I'm using a replication factor of 2. I will set up a pool of X number of machines, out of which the replication factor would be 2, because it can be 2 out of 2. So it will be like something extra more than that. Next time when I have to scale this, I'm paying an entire price of 2 terabyte. However, this may only be a small subset of my data. This may only just be 200 MB of my data. But because I have no ability of data locality of such flow control mechanism and they sit as a part of a vertical stack, my only choice is that either I go back, I create different lakes to be cost efficient, to be performance efficient, to be durability efficient, to be reliability efficient, or we now end up paying the same amount of money for whether or not that metric is important to us or not. This spray and wait is a very common as a phenomenon that you'll use everywhere. You will see that the strategy is very simple. Take data, distribute it. Now, when you query it, ask every single node, hey, do you got a copy of this data? Hey, do you got a copy of this data? Do you get a copy of this data? Which means the more number of shards that you add, because at some point you'll stop vertically scaling, you would have to add more and more nodes to it. Imagine a situation where you have 50 such nodes. Your every single query is basically doing a spray and wait. It asks every single distributor in the process and says, do you got this data? Do you got this data? Do you got this data? This is completely reverse of an anti-fragile system, which means when you're working on stress, when you're working at a scale where it matters, your performance actually degrades further. For toy data sets, it works brilliantly well. For a proof of concept, for benchmarking, this works really well. But when you really put the rubber to the road, is when they start failing. And it's too late to realize that, because that is the only way that is known to scale such systems. And that is the part of expensive scalability. What is the other flow control mechanism that we know? Is load balancing. It's a common phenomenon where we would say that we put in a load balancer in the middle, we send the data, it will go back to one of the healthy nodes, so we can take care of scale, at least availability that way. But you come to think of it, we really did not solve the data locality problem, because it may still exist as a problem. Veterans of the database world say that the only proven massive scale database pattern is sharding. That means multiple writer nodes. If you don't have those, you won't scale. That's a problem one cannot shy away from. And sharding is a very deep concept. It just doesn't mean that take data and just shard it. Let's cover the depths of the sharding that are actually required. Sharding typically would mean you have this data, a pile of data, a block of data that is coming in, and we see this in cubes. If you go back to that, I want you to imagine each one of these cubes as its record sets, those metrics that are coming in. There are destination servers at the back. These destination servers could be either compute units or could be storage as well. It doesn't really, the locality applies equally to both. You take this data set and you send it to one of those nodes, either to save it or to be computed as well if there's any processing required. Now, this requires multiple aspects to it. One aspect is splitting the data. You don't take the entire chunk and send it as it is, because that doesn't really buy out a scale problem. Because it will work in load balance mode, but it will not work in sharding mode. If it was load balance, you'll take the entire data chunk and you'll send it to one of those nodes. But think about it, that will be such an inefficient design to scale, because what would be happening is your entire data set needs to be processed or stored with one of those nodes at one point of time. For sure, concurrency will be solved. I'm not denying that. For sure, if you had 5 requests, those 5 could be distributed. But what about that one large request itself? Your single node has to be large enough where at least one request can house the system completely. Now imagine when a request packet comes in with that billion, which and you cannot have one large server for every single request. You'll be processing multiple of those. Each box gets this undue pressure of making sure that it can house at least one packet fully. And vertical scaling has a limit to it. And that is why these things don't scale. This data needs to be split. This data needs to be split in a predictable way where it can actually go into those each processing units. Now you may split this data based on range of values or based on a key in data. Range of values would be you read every value and you would say all values from 0 to 13 would go here, 13 to 26 would go here, 26 to 39 would go here. Or a key would be you basically take the key, another key of it. Let's say I want to process payment transaction or user IDs for that matter. Let's say Twitter X now, and all tweets that are coming in would be based on the key in the data, which is the user ID. We're going to split this data and so that it is processed or kept somewhere else. And that key would be a user ID. So basically, use an algorithm to make sure that okay, X number of users' data will go here, Y number of data will go here. So basically, you're predictably distributing the load across the system. Now, that's part number one. Second part is identifying the address. Now, the most simplest way that you would use many systems to use this methodology here would be a simple hash function. A simple hash function would be take the hash key that you have decided. I'm taking a very simple one, modulo it by the number of hashes available. Now, I want to double click on this problem here. Let's say we did this on user ID. We have number of shards as 2. User ID 1 comes in, hash 1 is generated. So it goes to the first server. User ID 2 comes in, and we basically do a modulo again, and 0 index comes, so it goes to 0th server. Same, 1, 2, 3, 4. Now, we realize that user ID 1 is Elon Musk, and user ID 2 is somebody else. What this resulting, and user ID 3 is another such celebrity. We realize that 2 shards are not enough to handle this data. Now, what we do is we decide to add another shard, but our hashing algorithm now fails us because 1 modulo 3 is 1, but 2 modulo 3 is no longer 0, it is 2. What that means is the locality of data has changed. What that means is if there's any processing happening, if there's any query happening, it must know I was earlier at 0th position as well, and now I'm at second as well. So if there's anything which involves more data, I gotta go 0 and 2. Or otherwise, we'll land into the same spray and wait problem. Because now you gotta ask everybody, hey, did you have this data? Did you have this data? A wrong choice of hashing algorithm would actually result in landing back into the same spot of the problems of spraying and waiting. So while we did the sharding, we did all the grunt work of setting up the design, everything, but we did not reap the fruit of it because our hashing algorithm was wrong. So it's very important to pick up this hashing algorithm. And at a database level, it becomes almost impossible to pick the right one. And this information, well, some people suggest a different way to solve this. You may start saving stateful tables. Stateful table would mean once an entry of a hash address has been generated, we start saving in a stateful table. Now think about it. We are talking about millions of metrics here. If all of that system has to be kept in a stateful table, at one point that stateful table is also a database that is going to choke, is going to have lock constraints, is going to have constant atomic operations, lock operations, which are going to be swap and load, compare and do, X and Y, because you're constantly reading an entry table, which is being read by hundreds and millions of constant processes which are running in the parallel in tandem with each other. And the size of the stateful table itself will grow. At what point do you decide to decommission something? If you drop a key from there, which is not being used, you may lose the address and you will land in the same problem. So it's not an easy problem to solve. In fact, it's a very complicated problem to solve. An alternate way could be you could use a computed value, which could be pick up the findmost algorithm, which says this is where the hashing algorithm would be, but it runs into the same problem. How do we solve the problem of number of shards which keep on going on up and down? So what we realize is picking the right sharding key is actually very important here because it may change data locality. It has to support repeatable hashing. It also, even if it's saved, it has to be a small hash table so that if there is a change, we do not go override the part of the system where this data is not going to be sitting at. Lastly, there should be some way for a user to input to add that as well. Now, this is where Levitate gateways again, they take a safe bet of making sure that all of these are taken care of. There's repeatable hashing. There's a small enough hash table which is maintained to make sure that when shards go in and shards go out, it doesn't add undue duress on it, which allows for performance at the end of the day, come to think of it, because we know the only finite number of nodes that we have to read data from. And this is possible because the default keys that we pick are actually cluster and or a metric name because they don't change in the life cycle. If there's newer metrics that come in, they find their own destination addresses. If the hash algorithm changes, the stateful kicks in. It takes care of the fact that the previous known state is legit and the next one will not be. And optionally, also give a user input label to it. Because many a times you may be saving data, which ensures that your partitioning scheme at your metric level is already taking care of this. In some cases, this may be a region ID, it may be a data center, it may be a partition ID as well. Or if you are a multi-tenant system in yourself and you're observing, then you may add a tenant ID because your observations are really apart. This allows us to build that sharding engine, which is actually pretty effective. And it allows to solve the data hotspot problem as well. Because by default, if there's a data hotspot, you can start coaxing that and actually solve for it. But data hotspots require constant monitoring as well. And while we constantly monitor, what this unlocks is a thing called localized scaling. Localized scaling is a concept which probably we have not seen it elsewhere. The part that I said, every single metric may deserve to function differently. Now, think about it. Number of tweets is a metric, is very important. Number of tweets liked. I mean, in Twitter's model, this will be a very good example, right? Now, if this is an instrumentation metric that is required, this is extremely crucial information. This is a high cardinality information. And this piece of metric as a sharding algorithm now can actually go to a separate storage unit of its own, which is this is a high performance lake that I have or a storage unit that I have, and this goes into those nodes which are going to be scaled differently. So the same database now can actually be scaled at a almost at a metric point scaling as well. Infrastructure metrics, small number of nodes. Business metrics, finite, large number of nodes. And that routing mechanism is actually available because the sharding engine can take care of it. That's what a good sharding engine can solve. Taking a recap of all of this, the Levitate time series gateway allows to solve for rate control, flow control, both at data and compute level as well, locality control, data and compute. In the next part of the talks, we'll actually cover those concepts as well. What does compute locality mean? And those are the aggregator units. For the interest of time, we may not be able to cover into this session. So go back to the layers. There's a Levitate time series gateway, which we just covered. Then there are others such in every single part of the problem, the ingestion pipeline, which was instrumentation, ingestion, storage, and query. There is a different amount of workflow that is required at each layer to be able to stay on top of this cardinality. And these are workflows which are above and beyond, which are way more than just picking up an off-the-shelf database and say this database scales infinitely. That statement is untrue, and so would your experience be. But why do we do all of this? Why do we spend all this effort into building these workflows which are fine? For a simple answer of a high cardinality workflow. This diagram will be available in the slide, but I'm still going to take a moment to spread this out, to spend time on this. When you start your day, you just want to look at, is there a cardinality warning? If the answer is no, go back to do what you're doing. Your observability lake is going nowhere. There's no problem to solve. Just don't look at it. But if the answer is yes, find out which one is the offending metric. It is as easy as day to find it out because the gateway actually reports here is a breach happening, here is a threat happening. Now, the next question that you ask yourself is, does this growth look legit? Don't jump onto scaling it. The growth look legit. You want to be able to answer this. And if it looks legit, you simply go and provision new capacity. There are ways to do this. You may move that metric into a separate scaled unit as well. If it is done, go back to doing what you're doing. If the growth does not look legit, you may have three choices to make. You may want to relabel this to drop the cardinality. You may want to drop the metric itself, or you want to drop a part of the metric, or you may want to aggregate as well. Aggregation means things of materialized views, which the relational database world has seen for ages and decades now. You may want to create those which are covered in levitate aggregator unit. Next question you say is, once I've taken this decision, did I act in time? Because obviously, as it is breaching and you're taking this decision, you may not have acted in time and the metric may have breached itself. If it has breached itself, you go back into the same loop. Do I need to provision more capacity or is the system stable now? If it is back into capacity and stable, go back to doing what you're doing. If it's not, provision more capacity. If you have not acted in time, go back to finding the offload metric and keep repeating the cycle till you actually get it right. This is the simplest workflow that you would actually live, and this is what we live with as well on a high cardinality workflow. Absolutely chaos free, deterministic, and at all points of time, you are on top of it. This is what these workflows can actually deliver. The only question that we leave you with is, once this cardinality is not a problem, what more would you do with this? What more would you start observing? Does it unlock for you the potential, the ability to actually start asking better questions to your system from your observability data? Looking back at the diagram, this is this, and we'll cover the remainder of it in the subsequent parts of this conversation. Thank you.
Awesome. That was a great overview, Piyush, of the internals of Levitate and how we handle the high cardinality. We have a couple of questions in the chat. So you mentioned about benchmark, and this is from Discord. So you mentioned about benchmarking and how system can work for the benchmark, but may not work in the real world. So do you have some thoughts on the benchmarking mechanism that is done and how it actually fares out in the real world?
You mean how Levitate fares in the real world?
Yes.
Well, it's a function of, it's like asking how well RDS performs. The more you scale it, the better it will work. The question is, after the conversation, after the talk, is there really a need to benchmark against trillion metrics? Or would you rather opt a high cardinality workflow and not scale it to trillion metrics because maybe you don't have to? That's one question I want to leave with actually, because more often than not, we find ourselves benchmarking systems because we don't have an answer to it. Remember, my CPU and my business metric are sitting in the same lake. So I'm forced to benchmark it. Oh, will I be able to handle a trillion scale? Do you have to handle a trillion scale again? Is that a real thing to be done? Now, that's the first question, right? Second answer to that question. Uh, Compare apples to apples. Of course, the amount of cost that it takes to actually ingest that same amount of data via our gateways is way lesser, and we'll find a way to publish those numbers. In fact, we'll be happy if the OP, whoever has asked this question, can tell us what to benchmark it against. Tell us the system that you want to benchmark it against. Tell us the cardinality that you're really testing it for, and we'll be more than happy to participate with you to publish those numbers.
Awesome. There is one question from Siddhant on LinkedIn. What approach would you suggest to handle high cardinality metrics that are essential for business? So, business metrics, but with a raw Prometheus and persistent storage setup.
Uh, what uh, I don't think you will be able to do it there. You need you need better workflows. You need long-term storage. You need like I just cannot imagine uh, a use case where I would have like first of all, I would probably use recording rules. Like when I have high cardinality, naturally the answer gravitate towards recording rule. And I mean, I'm almost shooting myself in the foot to advertise recording rule because the next talk that I cover, I'll actually tell you how recording rules don't work. But for a known construct that right now it is available, like recording rules is probably a better way to handle such thing because uh, think about it, right? Like let me do a quick maths here. Let's say you have a million metrics, million cardinality. Million is a very small number. We just learned that. You can easily hit million, right? 200 pods, 10 endpoints, 2000 already. Uh, 10 versions, 20,000 already. Environment five times, we've hit 100K. You know, see, I'm hitting a million on my fingertips right now, right? Let's say a million itself. A million samples coming in every single minute. Think about it. and you're going to make a query. You're going to make a nice dashboard. What are the two use cases you use it for? Alerting, dashboard. I run 6 queries. 1 minute alert, 5 minute alert, 1 hour alert. I run 3 dashboards. Very simple dashboards. 1 hour look back, 1 day look back, 1 month look back. Sounds legit? 1 million samples for a single minute actually means 60 million for an hour, which means 1.5 billion for a day. So every time you're refreshing your dashboard, you're actually throttling the database to scan 1.5 billion samples from your storage. Do you really want to do that? Those points are not going to change, man. They're going to remain the same. What has gone into the system has gone into the system. This is where we kind of take this for granted. If I throw this problem to a relational database guy, they say, no, 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 use materialized views. But because those constructs are missing in time series databases, we gravitate towards thinking, oh, it is legit and it is the required way to actually load 1.5 every time. 1.5 billion. Think about a month worth of data. We're talking about 45 billion on every single refresh of 30 seconds. Each one of those pretty dashboards out there with an auto refresh of 30 seconds is loading 45 billion samples each time. Waste of resources. Use recording rules. If you really must use Prometheus, please use recording rules. Save some money, use that money elsewhere.
Siddhant also has another
Buy
question. I
me a
think this
coffee.
was, yeah, sure. Yes. Piyush likes his coffee a lot, by the way. Siddhant also has another question. I think this was asked before. Piyush, you talked about the per metric cardinality support that Levitate has. But Siddhant is asking about, in case there are a lot of metrics being captured, do we set limits for each particular set of metrics or a general limit for all metrics? What kind of parameters should we consider while evaluating that limit? I think it's an interesting question
Absolutely.
because considering the
Yeah,
time series databases that are out there, the global limit versus per metric limit is an interesting question to answer.
absolutely. The trouble with global limits is, like one guy is going to eat that entire ration and then there's a blackout. And that is where joint families split into nuclear. Like, oh, I want to take my lake elsewhere. This doesn't work for me. I'm on a blackout because some guy stole entire cardinality quota of mine, right? Now, which is where this per metric thing comes in picture. Now, how to set per metric? Well, it's a function of your business need. You almost know your cardinality. Let me put it this way. High cardinality is an accidental problem. Bold statement. Trust me. Accidental high cardinality is a mistake. More often than not, the designer knows their cardinality. You very well know whether I actually need a million or a billion if you just do a simple back of the envelope mathematics. So when you know your cardinality, you know what to expect. And when you know what to expect, you can actually set that limit to that particular value and say, okay, this metric stays up to a billion. This metric only goes to 1,000. This metric goes this way. You don't have to do it all the more for every single metric. You can, when you're using Levitate Gateway, you can have a general one and you can have a specific one as well. But you more often than not, you know this. In
All
fact,
right.
it's a very good way of something that breaks your assumptions, your mental models. It's like let me ask the question the other way. Do I ever deploy a software and I come back, hey, I think I got trillion requests by accident? No, right? The one who built the software knows that, oh, I was expecting 1,000 requests, 10,000 requests per minute. I've never seen a developer who says, I built a system for 1,000 requests, but accidentally I got a 1 trillion requests. Never seen somebody say that.
All right. Looks like we are almost out of time as well. So Piyush,
Okay.
just want to ask one last question. What thing, like, can you give us a small teaser of what you are going to cover in the part two that you will be discussing next time?
Yes. Part 2 and 3, which is building Levitate aggregator units. Levitate aggregator unit is our second component, which basically allows us to build massively scalable materialized views, which are native from QL. So think recording rules, but with the beauty of not having to process all that data on every single query. massive reduction in the storage. Is exactly the same construct of materialized views of SQL world, which have been brought into time series world. And that's what limited aggregator units do. And we've seen massive reductions in toil and cost because of just being able to stay on top of high cardinality streams. While there's a limit to what you can store, there's a physical limitation. There is almost an unparalleled limit or lack of a limit into the compute aspect of it, because you can keep computing. Storage is going to be permanent. Compute is only when you're computing it the first time. And aggregator units fundamentally bank on this principle, right? So think about it. When you save 1 billion, you're paying for it for every single second that it stayed there, which is forever afterwards. But when you compute, you only pay for that computation while it was being computed. This arbitrage that happens here is a massive, massive gain. Yeah.
Perfect. And we'll be announcing the date for the next session pretty soon. So, like, keep looking at our LinkedIn and Twitter account. We'll be updating the schedule very quickly. Also, we'll be sharing the slides on the LinkedIn as well as Twitter stream. So, we'll also share a few resources and blogs that we have published around the same topics. Thanks a lot, Piyush, for your time, and we will catch you with you again probably in 2 weeks time, and we'll talk
Yes,
about the levitate aggregator unit.
we'd love to have feedback. Like whatever you want to get covered more, please reach out to us.
Yeah, Piyush, we just got one last question from Aniket, if you can handle that. Given a metric that hits cardinality limit and one label is the culprit, does the gateway stop ingesting all the metric samples and flags that metric, or a subset of samples that were problematic?
The choice is yours. It can allow you to do it either way. It's a it's a configuration. It's a lever that sits in your hand. Like when you use Levitate, I want you to imagine yourself like being that operator pilot. Like I always have this thing. When pilots sit in an aircraft, have you seen the amount of buttons that they press? It's like it's been 50 years. Why can't you just press one button to say on, off? Yeah.
Awesome.
So yeah,
Awesome.
cool.
I think Aniket, that answers your question. If you have any other question, feel free to ask, and we'll answer that later. But thanks a lot, everyone, for joining us. We'll be back again with Piyush discussing about the Levitate aggregator units. And please share feedback. I will be sharing the slides as well as the blog posts in the comments. Looking forward to all the feedback. Thanks a lot, everyone. Thanks, Piyush. See you next time.
All right, bye.